negative, or 0? What happens if k is 0?
B is whatever.
It's just b. And then it's true. See, yeah, it's tricky, it's tricky. So, so this, let k equal 0, and this is true. Because we already have b greater than or equal to 0. Make sure does that sound good? Yeah. Okay, so now we're gonna have fun. Now we're gonna get into the territory you were thinking about where we need to pick something else. So the case where b is less than 0. So check it out, like b is a negative number. Let's just, a little scratch word here. Let's just say like b is negative 17. So I got negative 17 plus some positive number, that's a, because a is positive, times k, and I want that to be greater than or equal to 0. So now, Nathan, your idea of picking a large enough positive number for k is totally going to be the way to go. Check it out, because I got a negative here. This is positive. If k is positive and I pick it big enough, this is a super big number. Let's just let k equal, 10 to the 10th. Sweet, super positive, right? So we could argue that way, but we could be more precise as well. So check this out. We're going to let k equal, let's see, so we got a 2b. Yeah, 2b. So I'm yeah, 2b. So check this out. Wait, I didn't put the case up. Sorry. So here, case b is less than 0. Sorry, I jumped ahead. So now we're looking at the next case because we already got that case there. And so when this k is a super, what did I write over here? What did I have? Bless you. So we got b is negative, some blesses, many blesses. So we've got times a positive. I've explained this to myself like about a dozen times, and suddenly weirdness is happening. Oh, yeah. So to make this whole quantity, we're subtracting, we want this whole quantity to be positive. This has to be a large magnitude negative number, so that when I multiply it here, but then subtract it off, it becomes addition. Yeah. So what I'm going to do is set k equal to 2b. Since b is already negative, that's a negative number. So note, this is negative. And when I compute the quantity b minus ak, it's going to turn into b minus a times 2b. And that's going to, I can factor out a b. I get that. So now we need to convince ourselves that this is a non-negative quantity, so that this thing is actually an S. Can anybody maybe tell me why? Why is that non-negative? Sydney, I see your hand. Manipulating.
So because b is negative,
Yeah.
anytime you multiply a negative times.
Yeah. So why is this negative? Because it is. Why is it negative?
I was working on that.
Good, cool, good. Oh, good. What do we know about a? A is an integer greater than 0. So what are integers greater than 0? So a must equal like what? Where does it start? 1? Beautiful.
Oh. So because if you're at least subtracting 2.
Yep.
So it's always negative.
Perfect. So this thing here, because a is at least 1, this quantity is at most negative 1. So let's write that out. Because a is greater than or equal to 1, 1 minus 2a is less than or equal to negative 1. So I got negative times negative, and it's positive, and yay. So that means that if b is negative, there is something in S. And that's all I really care about. If b is non-negative, there's definitely something in S. There's B. So we're good. S is non-empty. And we can now invoke, I'm not going to worry about my WD-40. Now we can invoke the well-ordering principle. So by the well-ordering principle, there exists a least element in S. And we're going to call it, what was it over there, Nathan? You told me it was the remainder, right? Yeah. So we're going to call that R. Let's call it R. So I've got this R, it's the smallest element in S. So that means for some K, A minus BK is equal to that R. Over here, the K was 3, but we don't know what it's going to be in general. Is this making sense? Yeah. You good, Diana? Yeah. So, is this starting? And let's actually, for some K, let that K be Q. It's just some value. I'm just relabeling it, but I mean, hell, look at the result, right? We got to get that Q in there. So whatever this least element is, for K, that's actually the divisor, and then the R will be the remainder. So let that K be Q, and we have A minus BQ is equal to that R, i.e. good old division algorithm. Oh, it's ass backwards, isn't it? Did I change? Oh wait, shit, sorry. I wrote this backwards. Okay, it's all good, it's all good. B minus AK, sorry. Whew. B minus AK. Just trying to keep my letters straight. So i.e. B is equal to AQ plus R. So that's the first part of this. We got that. Now I need to show 3 other things. Well, actually 2 other things. I need to show that R is less than A, and I need to show that these 2 R and Q's are unique and there's no other pair that works. So we've got the existence. So this is the existence portion. So now we're going to show that R is less than A. We already know R is greater than or equal to 0 because it's equal to something in that set S. All the stuff in S is greater than or equal to 0. So here, let's make a little note. This is true because R is in S and everything in S is greater than or is equal to 0. So that's cool. Now we got to show this, and this is best approached through contradiction. So to show R is less than A, assume it's not, and wind up with something foul. Wind up with a contradiction. This might be a place where I call you in, so follow along. I might ask, what was the contradiction I just produced? So we've got R is greater than or equal to A. So I'll just start that up here so we have a nice fresh line. Well, that implies that B minus AQ is greater than A. Or greater than or equal to A. I'm just replacing R with what I know it's equal to. Are we following? Good. Nathan, yeah, please ask.
In the bottom one, show like R is less than A.
Yes, sir.
Assume R is greater than A.
Yeah, so what we're going to do is we're going to show, I'm going to assume that if R is bigger than or equal to A,
something contradictory happens, so that this is actually impossible.
Okay.
Does that make sense? Yeah, cool. Thank you for asking. Awesome. So let's check this out. Well, let's subtract a off of both sides. Greater than or equal to 0. Here I can pull an a out. So now check it out. I've got b minus a times an integer is greater than or equal to 0. This is, do we agree that this is an integer because q is? Yeah. So this is an integer, and it is non-negative, so it must be an s, because that's what s looks like. It's all the stuff b minus a times an integer that's non-negative. So b minus a q plus 1 is in s by definition of s. However, so here's the contradiction coming up, but b minus aq minus a has to be actually less than b minus aq. Why? Well, actually, strictly less. Why is that true? What do you know about a? It's not on board anymore. WD-40, come on, bro. I'm disappointing. Let's not speak of this. That's all, it's just us. The WD-40 crew here.
It was a good experiment though.
It was, definitely. I'll probably try it in every class just to see what happens, you know. N equals 1 is a bad statistical place to go. So why is that true? Where the hell is it? Oh, right here. Why is this true?
A has to be equal or greater than 1.
Yes, yeah, because A is positive, right? And certainly we know it's greater than or equal to 1. So if you subtract a positive off of a quantity, it becomes less. So this is true because, and I like the way you said it, Trinity, because A is greater than or equal to 1. So you subtract 1 off, it gets smaller. Subtract more off, it's even smaller. Why is that a contradiction? Where's the contradiction? Yeah. So I've got a new smallest element in S that's different than the original one. So let me help you out. Let me point you. This was constructed to be the smallest element in S. But it's not anymore. And it's not anymore, and all of that was a result of this assumption. So as soon as I assume this, I can actually, I can produce a new smaller element in S that's different from that first one, and that's a contradiction. It's breaking that first assumption. So this is a contradiction of the construction we started with. So this contradicting the assumption that B minus AQ is the smallest in S. So that means this is a foul thing, that this cannot stand. So we say nope. Thus, R has to be less than A, and we have our main part of our result. Now the uniqueness is going to be real easy. So thanks for sticking with me here. And B is equal to AQ plus R, and we have this condition as well. So lastly, let me stop. Is that any questions on this proof? questions here, my friends? And we can always come back. So let's knock this out. Lastly, we show that Q and R are unique. A little scooter board, maybe a skateboard. Actually, be kind of cool, you know, right? Just like.
I'd pay to see that.
Would you bring me a skateboard?
I don't know how to skateboard.
I don't either, and it's how I'm still in one piece.
Y'all wanna get him a skateboard? It wasn't a choice.
Yeah, I don't.
No, it wasn't.
Good.
I never played this.
That's good, that's why we're all intact, right? We're math people,
I have one at home.
Trinity,
Do
bring it
you?
in.
Are you a boarder?
No, but I have one at
You should
home. I
come.
went through a phase when I was like 13. So,
It could come in handy now.
If you bring it, I will ride it,
okay. So I can
but no pressure, no pressure. That's a lot to lug. So what we do to show uniqueness, this is a classic way to show uniqueness. You assume that there's two things that do it, and then show that they actually have to be the same thing via all the other properties and assumptions you've already used. So assume that B is equal to AQ plus R with this caveat, and that B is equal to AQ prime plus R prime, where that R prime is less than A and non-negative. And we're going to show that Q and Q prime and R prime have to be the same thing. So, pretty quick, subtract. Subtract the two to get, so I'm just literally subtracting straight down. So B minus B is 0. Tell me if this looks okay. When I subtract AQ prime from AQ, I can actually kind of factor out that Q. Is that cool that this minus that is also that? Just think distribute that A, and it's a, and then I've got plus R minus R prime. Now I'm going to shift this to the other side, so I'm going to have R prime minus R equals A times Q minus Q prime. And I'm going to slap absolute values on here. Yeah? So I mean, was that like
You're good.
stunning or?
You're good.
Okay, all right, cool. So take absolute value of each side, and we get absolute value of R prime minus R equals absolute value of A, and I'm kind of using a property of absolute value of products here, just to pull that out. Okay, cool, so we're almost done, we really are. Good, that's good. We have a finite amount of time together. So notice that R and R prime live between 0 and A, and they can't get to A. So let's just draw a number line here. Here's 0, here's A, and I'm gonna put a circle on that because I can't get there. And then R and R prime live in here somewhere. What is the greatest distance between those two? What is the most this could be? Let's make it easier. This might be a little tough. I've got 2 points in here. Here's 0, here's 10, here's a point X and a point Y. What's the furthest these two can get from each other if they have to live in there?
Less than 10.
Less than 10, perfect. So this difference here, these two can't be further than A apart. Like the worst case is this one's down here, one's down here, and one's edging up to here, right? But they still can't get more than A units apart. So this thing right here is less than A. And A is a positive number, so check this out. So this is less than A. This is actually equal to A. So now what I've got is an inequality that says this. A times Q minus Q prime, so I'm taking that side, is less than A. A is positive, so I can divide. And we've got q minus q prime is less than 1. Why are they the same then? Why are q and q prime, why do they have to be the same thing? If that is true. Think about what are they? What set do they come from? They're integers. So if two integers are less than 1 unit apart, what's the option? They're the same, right? They have to be the same. If I've got two integers, here's my integers, they are less than they are less than 1 unit apart. That means they have to be the same. So because, sorry, this is getting a little shitty down here. Because q and q, oh no, I'm not doing that. Because q and q prime are integers, they have to be, that difference must be 0. But q and q prime are in Z, so q minus q prime in absolute value has to equal 0, i.e. q is equal to q prime. Once q is equal to q prime, this is 0, and r minus r prime is now 0. And then, so it follows that q minus q prime is equal to 0, i.e. q equals q prime. Good Lord, may we never visit this again. But thanks for staying. I appreciate your company in these spooky times of math. Haunted math house. Okay, we've got the division algorithm. Yay! Now we can use it, and we will never speak of this proof again.
Good.
Okay. Right. We don't talk about WD-40. We don't talk about this proof. We've already got this nest of secrets that we're building. Like what? Like Fight Club? Yeah.
Fight Club.
Yeah. All right. So division algorithm, we got that. I learned a trick just yesterday. Do you know how to tell if a number is divisible by 7? I didn't either. so like knowing when numbers are perfect, some are easy, like I know when a number is divisible by 2 because it's even. I know when it's divisible by 5 because it ends in 0 or 5. You know, so there's certain things that are pretty easy. Does anybody know any other divisibility tricks?
By 0.
What's divisible by 0?
0.
No! Befouled! But I know you're just messing with us, trying to wake us
I
up.
actually didn't mess this up.
0 is divisible by anything, but that's a black hole, some sort of wormhole that we go down and the universe implodes upon itself.
Okay, I thought that was 1.
Well, let's follow this. I like that. Oh yes, I love this. So if I multiply both sides by 0, certainly that's true, right? Get that, yeah. But what if I take this equation and I multiply both sides by 2? So I take this equation here and I multiply by 2, so I've got 2 times 0 over 0 equals 2. But 2 times 0 is 0. So this is still 0 over 0. So now I've shown that 2 equals 1.
Okay.
That doesn't sound good.
That makes sense.
You can't go. I'm so glad you asked though. Thank you. Thank you. I appreciate your participation.
Probably go back to the basics.
It's okay. The good news is everybody here is going to be starting with fresh basics. This shit here, we're not even going to mess with this. We're going to wish we had 0. No, we're going to have so much fun. All right, let's see. Let me check my notes and see if there's anything I wanted to tell you betwixt this and the next result. Oh yeah, let's do some experiments. So use the division algorithm to divide 30 by 7. Can you do that for me, please? So write out the, 30 equals something times 7 plus the remainder. What goes in those boxes? Remember, this must be positive, so the thing in the box has to be positive. Anybody got some numbers for me?
4 goes in the box,
Get you up to 28?
and then 2 goes in the triangle.
2 is a hot remainder today, right? So pretty cool. So yeah, so we put a 4 in the box, the largest multiple of 7 that fits in here, right? And then we put a 2 here. Awesome. Now let's divide negative 30 by 7.
It has to be positive.
Oh, sorry. Yes, that is actually, sorry, thank you, Nathan. That is absolutely true. The thing that we're dividing, this is the thing that has to be negative, so I screwed up. The thing we're dividing into the other one we assumed.
Oh, okay.
Right, yeah, so thank you, really good catch. So we've got negative 30 equals something times a positive 7 plus yield remainder. This one's a little trickier. And the remainder has to be non-negative too, right? So this is also, this has to be non-negative. And less than 7, so this little dude right here. Thing in the box will have to be negative, right? That's kind of a little clue. You got something, Diana?
I was thinking -5.
Well, I think I like the sound of that. Yeah, exactly. So we kind of have to overshoot it, right, to the left. So when we think about it, this is the quantity that is closest to this thing from the left side. And that's a good way to think about that. So yeah, so you put a -5 in here, that gets you -35 and allows you to have a positive remainder. Great job, awesome. Make sense? Yeah, tricky too, kind of a little counterintuitive. More divisibility fun. Let's get a couple definitions up. Definition. Given two integers a and b, the greatest common divisor, which will also be another super prolific, prolific is a concept we see all the time. A and b is the largest k, which is an integer, such that k divides a and k divides b. And we write here, denoted by GCD of a and b. And let's just do a couple. So GCD of 24 and 30. Anybody have any, remember any ancient primal algorithms for even figuring out what this is? Because here you could probably like just go through and work it out. It's still hurting my brain a little for some reason, but I think I got it. What do we think the largest common divisor of those two is? By yes,
Okay.
thank you. Yes, I always clarify my scribblings, yes. So denoted by GCD of AB, kind of like a function. It is a function, yeah, of two variables. What's the largest common divisor of 24?
6.
Oh, beautiful. You're much smarter than me because I had 3 in my head. So good job. Okay, you and me. We're all right. We'll help each other on the skateboard. Make sure we stay safe. Okay, so good job. Thank you. Yes, you can. You don't have to attend anymore. You're done. But there's a nice algorithm for doing this. So an algorithm. I'm going to actually show you a couple algorithms. So algorithm 1 is use the fundamental theorem of algebra. Did anybody do any of that reading in chapter 0?
No.
Does anybody know what the fundamental theorem of algebra is?
No.
Yeah, fair enough. Every integer has a prime factorization, a unique prime factorization. So that's, yeah, you knew it. You know that fact. It's just maybe you didn't know that's what it's called. So algorithm 1 is find the prime factorization of, of each integer. And so it's probably easier to do this with just a specific example. So for 24, here's how I do prime factorizations, by the way. I just start dividing by primes, working from the bottom up. First prime is 2, got 12, 2 still goes into that. I got 6, and then 2 goes into that, and I'm left with 3. So I've got 2 cubed times 3. And then 30 is going to be, let's just do 30 that same way, 2, 15, 3, 5. So what I do now is take the intersection of those factorizations. What factorization is in common to both of these? And this makes it so easy. So you go through each factor. I can only use 1, 2, so the GCD is going to equal 2 to the first, 3 to the first, that's in common, and then no 5s because this one doesn't have a 5 at all. So this is equal to the intersection. That's like not exactly right, but I hope it kind of is suggestive enough. Factorizations. Had I done that, I would have come up with 6 like Sydney did. So that's a decent way to do it. I've got a much cooler way to do it, so much cooler. So let's get to that. And I want to get through this today, for sure. So the GCD is a theorem. Given A and B, and let's just say they're positive numbers. This makes life so much easier. The GCD of AB is equal to A times S plus B times T for some, and we might not, actually I don't think we need this restriction. These are just integers. So let's just do that. The GCD is equal to a linear combination of those two numbers for some integers. So an integral linear combination gets you there. Now that is just weird. And this isn't something you hear until you're here today. It's like once a year at this time, a group of people learns this fact, and nowhere else is it being learned. It never has been learned. Well, except in every other abstract algebra class. Let's not go there. So, that's cool. Let's prove it. Oh, bet you don't get shocked when I write a set S. So S is equal to the set of all linear combinations. So that's AK plus BL, where AK plus BL is greater than 0, and K and L are integers. Okay, so it's kind of like that first S, but here I'm requiring strict positivity. I don't get to equal 0 because we don't get to have 0 as a divisor. We talked all about that. Having 0 as a divisor destroys mathematics as we know it. We're done. Class over. So we've got this going on here. Let's look at a quick example. Let's say that, like, what does this thing look like? Let's use these two numbers over here, 24 and 30. So if A equals 24, B equals 30, what does S look like? Now, the way, a nice way to see S is to make, since you've got two inputs, you got a K and an L. Kind of make a little table here, and then this whole thing is going to be 24K plus 30L. That's what I'm going to put in the table. And so let's pick some. So here's L is 0, here's K is 0. Then we won't go too crazy on this table because it's actually an infinite table. There, but just to get a sense of what this thing looks like. Yeah, okay. I kind of wish I picked a different A and B, but it's all right, we got it. So when we have K is 0 and L is 0, I've just got 0, right? This quantity is just 0 here. And so that actually is not going to be in the set. Let's just figure out where the set might go. So let's see, let's fix L as 0. So I just got 24K. In this row, it's just 24K. So this is going to be 24 when K is 1, negative 24 here. And you kind of get the rhythm. It's just going to be multiples of 24. Like that. Does that make sense? Yeah, awesome. Yeah, awesome. So then up here, in the row above, I've got L is negative 1. So I'm going to actually subtract 30. I'm taking 30 off of this row. So this is just going to be negative 54, negative 30. Good Lord. Thank you. 6. And then, say, what was it? 18. Thank you. Thank you. Yeah, that's beautiful. That's really beautiful. So check it out, none of these values are in S, but this one is, right? So this one is in S, so like right now we're kind of seeing what where doesn't begin there. S begins here, right? It's on that positive side, those output values that are positive. And then let's just go to this next row, and I'm just adding 30, because L is 1 now, so ooh, I can do it. 6. Ooh. That's our GCD, right? So what am I adding? I'm adding 30, so 30, 54, and then I don't know, shit. I guess that's pretty easy. Just stop being lazy. Me, stop being lazy. And then let's see, so when we move this way, we subtract 24, so this one would be like negative 18 to the left, right? So we're seeing S unfold. Let's actually go to the 2 really quick, just to kind of see what's happening here. So again, when I move to the next row, I'm going to add another 30. So this is 36, this is going to be 12, this is going to be 60, 84, 108, blah, 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 and good Lord, that thing just continues onward and onward. What's actually to the left of this negative 12? Positive, yes, sir. Yes, I do. Thank you. What would be the left of that guy? Negative 12. Because I'm subtracting 12. Wait. Yeah, I'm subtracting 24 off. Okay. Yeah. So, check it out. Right now, I'm getting a sense of what that set S looks like. And I've seen a lot of big numbers, and I'm noting that the smallest one I see so far is 6, which just so happens to be the GCD. So that's our claim. So claim, the GCD of A and B is equal to the minimum element in S. Cool. Let's prove it. And this was just like motivation for why whatever mad woman, mad person created this. They must have looked at something like that, because it seems completely counterintuitive to me. So, proof. Let D equal the smallest. Oh, first off, we have to show that that element exists. Proof. First we show that there is a smallest element. What do you think we're going to invoke to show there's a smallest element? The well-ordering principle. I got a set of integers. They are positive integers. Everything in here is positive, so the well-ordering principle is going to give me the existence. First we show there exists a least element in S. So to do this, invoke the well-ordering principle. Exclamation point. Very exciting. So just need to show S is not empty. This means, and this is much easier than our last time. We just need to show S is not empty. So let's take a look at S again. S looks like this. Maybe you might not need to write it all again. It's just freaking right up there. So A and B are going to be, should they be positive? No, it's not. Should be positive. Well, I just want to make sure neither of those numbers should be 0. That's for sure. Let's just make sure we put that up here. Let's just talk it through. So, if A and B are just some integers and they're not both 0, which would be a weird thing anyway for us to be considering, if A and B are not 0, do you believe that there's some K or L that makes this quantity non-zero? Can we believe that for a given A and B that aren't 0, there's some K and L values that make this non-zero? I mean, surely it can't be 0 for all K and L, right? So I give you 2 integers. I know for a fact this can't be 0 for all K and L. In fact, I could even just, if I let K equal -A and I let B equal, or I let K equal A and let B equal, L equal B, then look what I've got. I've got A squared plus B squared, and that's a positive quantity right there. Actually, that might be good enough. I think that's good enough. This isn't where I was going to go. But does that make sense that if I've got A and B and they're not both 0, all I have to do is basically take the square, make sure I'm taking the square of each one, and pick the right K and L. So choose K and L like this. And then this is greater than 0 if A and B are not both 0. Does that seem reasonable? Yeah. So now we've got S is not empty. That wasn't the way I was going to go. The other way I was going to go is if you pick some K and L and this quantity is negative, just take their negatives and it makes this thing positive. So there's lots of different ways to see this set is not empty. Okay, so S is not empty. Cool. Therefore, the well-ordering principle implies there exists a least element. Let's call it D. That's going to be our GCD. Let's prove it, and then we'll be done for the day. And then Monday I'll show you a nice algorithm for demonstrating how to find the GCD, a really cool algorithm that uses the division algorithm, really wild. So just need to show that D is equal to the GCD of A and B. And so there's two things I need to show. First, that D divides A and B, and that it's the greatest thing that does. That if anything else divides those two, it also divides D. So part one is show D divides A. Oh God, okay, I'm sorry, I have to go to the restroom. I've been like trying to like make it, it's just not gonna happen comfortably. I can't do algebra in this pain. I'll be right back. I was gonna try to push through. Thanks, friends.
Yeah. His quizzes are always super easy. I had him for linear algebra last semester.
Last semester? Or last year? Or fall?
Last year. Was it last year? When did I take linear algebra, Diana?
Fall
Last
away.
year. Yeah, fall.
Okay. Because I took it last semester. You weren't that class.
Oh yeah, you're sorry. What did I take last semester? Oh, fucking differential equations.
Yeah.
Yeah.
How was that class?
Dog water.
It was miserable.
Yeah, don't.
Who do you have?
Devolved.
Post Devolved.
No.
No.
Okay.
If you can avoid taking classes.
Yeah, don't.
My friend's taking linear algebra with her.
Oh, rest in peace.
Yeah.
Rest in peace.
Yeah.
Calc was super easy. She retired.
Who retired?
Calc.
I love her.
And,
Oh.
do you guys know if you have like to take logic and proof for this class? Because I haven't taken that class.
Is logic remember prereq for this one?
I don't think
Oh,
it
that's
was.
good.
I think it is.
We're doing a lot of proof, yeah, okay.
I would,
But,
based on that, I would assume so.
but it's pretty easy to catch on, I'd say, based on just how he formats
Yeah.
his proof. If you do it like him, then it's
Yeah.
Okay. I'll probably go. Yeah, I'll ask him.
Because I think that's the one that I had to take to be able to take this one.
I took that class so long ago. Logic and proof.
I'll just sign up for shit and hope he says
Yeah.
it's okay.
Well, cause it doesn't stop you. to
Yeah,
Sign up for any class, you can sign up for whatever you want.
Yeah.
it's just very
Logic and
helpful.
proof is not
Yeah.
available this semester.
Oh, next semester.
All right, all better. Like a new man. Thanks for understanding. We're friends. This is okay. So we're going to show this. So by definition of D, the way we pulled it as the minimum element out of S. So since D is an element of S, we know that D is equal to AS plus BT for some S and T. Right, because that's where it came from. It's from this set here, so it's got to equal that for some particular integers. And we're also claiming it's the least such element. Good, yeah. Okay, so to show D divides A, let's employ the division algorithm. So that would mean if I divide A into D, A is equal to some multiple of D plus a remainder. And that remainder is non-negative and less than D, the thing I'm dividing by. If R equals 0, huzzah, I'm done, right? If R equals 0, then D divides A, and I'm good. So if R equals 0, A is equal to QD, and that's literally the definition of D divides A. So let's assume not. Assume R is greater than 0, but also strictly less than D. And that's where some problems are going to come in, kind of like last time. Okay, well, take this expression, rewrite it, and we know that R is equal to A minus QD. And since R is assumed to be greater than 0, this is greater than 0. Yeah? And so it's in S. So A minus DQ is an element of S. Furthermore, I'm assuming a very particular structure about D. D looks like that AS plus BT. So since D equals AS plus BT, this expression, A minus DQ, is equal to A minus AS plus BT. Whoa, whoa, whoa. Pause. Whoa, whoa, whoa. Wait, am I okay?
I think you're right.
Is this okay? I think that this, I guess that kind of is in S, right? Because you could just have K equals 1, and yeah. I think I was going to, I think the following thing was about to show me that it was in S, but let's just keep going. What the hell? Times Q, whatever. And then, so this is A minus QAS minus QBT. Some algebra, right? And so this, we don't know it's in S yet. We don't know it's in S. What a dumbass. Fucking idiot. All right, so this isn't it. We just know this. And because the stuff in S, it has to be A times something plus B times something. Yeah? So this is, we don't know that this is an S. We're about to see that it actually is, but we didn't know that before. So, the only people I would ever call a fucking idiot are myself and my friends. My friends I play video games with. And for some reason we find that hilarious. We call each other that. So this is actually A times 1 minus QS plus B times negative QT, and sure as Shinola, that is in S because it's positive. So remember, this is equal to R, it's greater than 0, and so here, look, it matches the rhythm. This is in S. What's the problem? But, oh, yes! This is couldn't be a second earlier. Okay, but it's also equal to D, right? So this quantity, oh wait, no, it's equal to R. So this is R, right? But what do we know? We know that R is less than D. So check it out. I've got this new element, but A times 1 minus QS plus B times negative QT is equal to D, equal to R, and that is less than D. So I've got this thing in S that's less than D. What's the contradiction? We've been here before. D was the smallest element in S, but I just produced one that's smaller. And what made that possible was assuming that R was non-zero. So the assumption that R was non-zero led to a contradiction of a smaller element in S, and that's bullshit. So no. That's bullshit. Because D is the smallest element. Yes. So R has to equal 0. Boom.
Sick.
It is sick. It's sick and insane. Sick and insane. Just crazy. So I would ask you to just read the rest of this proof in the book and just see why So actually, first off, the thing that D divides B is basically this whole same argument with A replaced by B. Same thing. It's boring to do it twice. And then you need to show that if there's another divisor of A, so like a D prime that divides A, it also divides D. So that this truly is the greatest common divisor. So if I have another divisor of A, if I have any other divisor of A, it divides D as well. D is the queen of all the divisors. So just read the end of that. I'm going to assume you did. And then Wednesday we'll have some more fun.
Monday?
Monday, yeah, thanks.
I'll be here Wednesday too, but like.
Yeah, cool, me too. So we have an assignment and the current due date is Wednesday. As of now, I don't have a sense that anyone has started that assignment. So what I would love is to talk about it on Monday. So please check it out, and then Monday, and you will find that I talk about things as long as we need to talk about them, right? Is this true?
Yes.
We will, hopefully we'll be past this by the end of the semester, but if we're not, I'm okay with that. Nobody's gonna be back if we're talking about this like for 3 months, 4 months.
You got like 3 weeks, best I can give you, Dr.
Yeah, me too, tops here. I might
Best I can
have a
do.
skateboard accident. Laid up. Thank you, friends. And let's see, let's get the assignment. I did mention it in the recording, but why not just get it to you right now? So it is, it's kind of hard to read up here, but it's chapter 0. Sydney, great to see you, friend.
It's good to be
So
here, Dr.
glad you're
Chelsea,
here.
next
Awesome.
week.
Yeah, go ahead. If you can read that. Okay, so it's just chapter 0, 2, 3, 4, 7, 14, 37, 38, and then this problem here, which may or may not be intelligible to you. It's 5 to the 1,000th mod 4, and 4 to the 1,000th mod 5. And we'll kind of talk about how to do that on Monday. So I kind of got a feeling this assignment's already getting pushed back.
So, are we going to like a couple problems on every chapter or?
Yes.
Okay.
Yes, absolutely. Yep, the assignment's no longer due on Wednesday. So, that sounds like me too. So, yeah, things are the same. Things change, things stay the same. Trinity, have you run into Dr. M at all?
No.
I was gonna say, if you see him, do me a favor and ask him if he's seen me lately.
Okay.
I'm telling people to do that so I can start to like kind of hit him from other sides.
Okay.
Yeah, did you have something you wanted to chat about?
I'm not gonna be here in class on Monday.
Absolutely.
Yeah.
Or just let me know if you need anything, if you have any questions, we can get together and figure it out.
Okay.
Okay, awesome.
I'm probably not gonna bug Dr. M until next week.
Not gonna
what
what?
about honestly?
Bug Dr. M until next week.
Oh,
Cause I wanna check in with like our honors seminar that we have on Friday first to see, cause we're supposed to be gauging how well we did with our summer progress. So.
you did stuff?
I mean, I did. I heavily annotated 4 books.
That's
so
intense,
that feels
actually.
pretty good.
It's way more than, honestly, it's one of the
Still
largest
recording.
contributions toward an honors thesis I've ever heard of over a summer.
Okay.
So.
And I mean, like there's not a lot of research to do when you're doing a pop culture thesis on something very, not strange, but like very particular.
Yeah.
So I'm gonna have to ask them again, like, hey, how much academic fundamentals out of this? Cause
Whatever you do, here's the secret. Whatever you do is gonna be fine.
okay.
Because it's really up to your advisors. The problem is you're not doing a math thesis. No one reads those. That's like when you do a math honors thesis, like the mathematicians that you're working with help you, and no one else knows what the hell it's about.
Yeah.
They just assume it's right.
Yeah.
Yours is like not that. So somebody might read it.
Do you still wanna be a reader?
I would love to,
Okay,
if you want me to be.
sure.
I'm assuming you're asking for that reason. So.
I mean, yeah.
You were hoping I'd say no, so you
No.
brought it up. No, I'm kidding. Yeah, I would love to.
Okay.
Absolutely. Thank you.
Do you still want to record? Yeah.
Yeah, does it need to stop it, Diana?